The universe is a vast and complex place filled with wonders that stretch beyond our imagination. From the smallest particles to the largest galaxies, every element plays a role in this grand cosmic dance. Yet, beneath its apparent chaos lies a deep and elegant order, a hidden structure that governs the behavior of everything within it. This order is not immediately obvious, but it reveals itself through careful observation and study. This order is revealed through the laws of physics, principles that govern everything from the smallest atoms to the largest galaxies. These laws are the language of the universe, a set of rules that dictate how everything interacts and evolves over time. Among these laws, one stands out for its simplicity and power: the principle of least action. This principle is a cornerstone of modern physics, providing a framework that unifies many different phenomena under a single, elegant idea. This principle asserts that nature, in its infinite wisdom, always chooses the path of least resistance. It is a principle that can be observed in countless ways, from the flow of water in a stream to the flight of a bird through the air. Imagine a ball rolling down a hill. It could take any number of paths, but it always follows the one that takes the least time and effort. This simple observation is a manifestation of the principle of least action in action. It could take any number of paths, but it always follows the one that takes the least time. This principle is not just a curiosity, it is a fundamental law that applies to everything in the universe. This simple observation hints at a deeper principle at play. The principle of least action suggests that the paths taken by everything in the universe, from light beams to planets, are not random, but are determined by this principle of efficiency. The principle of least action elevates this idea to a fundamental law of physics, suggesting that the paths taken by everything in the universe, from light beams to planets, are not random but are determined by this principle of efficiency. It is a principle that has profound implications for our understanding of the universe. This principle is not merely a mathematical curiosity, it has profound implications for our understanding of the universe. It allows us to predict the motion of objects with incredible accuracy and provides a unifying framework for seemingly disparate physical phenomena. It allows us to predict the motion of objects with incredible accuracy and provides a unifying framework for seemingly disparate physical phenomena. This principle has been instrumental in many scientific breakthroughs, from the development of classical mechanics to the formulation of quantum theory. The story of the principle of least action is a testament to the power of human curiosity. It is a story of brilliant minds wrestling with nature's secrets, of daring hypotheses and heated debates, ultimately leading to a deeper understanding of the cosmos. It is a story of brilliant minds wrestling with nature's secrets, of daring hypotheses and heated debates, ultimately leading to a deeper understanding of the cosmos. This principle has been a guiding light for scientists throughout history, inspiring countless discoveries and innovations. This is just the beginning of our exploration. The principle of least action is a gateway to a deeper understanding of the universe, a key that unlocks many of its mysteries. In the following sections, we will delve into the history of this remarkable principle, tracing its development from ancient Greece to the present day. We will explore the contributions of great thinkers like Euclid, Newton, and Einstein, and see how their work has shaped our understanding of the universe. We will meet the brilliant minds who championed it and explore its profound implications for our understanding of the universe. Join us on this journey as we uncover the elegance and beauty of the cosmos, guided by the principle of least action. Our journey begins in the 17th century with a seemingly simple problem that sparked a revolution in physics. This problem, known as the Brachistochrone Problem, challenged the greatest minds of the era to think deeply about the nature of motion and the forces that govern it. Imagine 2 points connected by a curved wire. The question posed was deceptively simple. What is the fastest path for a bead to slide down this wire under the influence of gravity? This seemingly straightforward question opened up a world of complex mathematical and physical inquiry. The challenge was to determine the path that would allow the bead to travel from one point to another in the shortest possible time. This is the famous Brachistochrone Problem, a puzzle that captivated the minds of the greatest mathematicians of the time. It wasn't just a theoretical exercise, it had profound implications for our understanding of the natural world. Galileo Galilei, the renowned Italian physicist, was among the first to tackle this problem. His contributions to science were already monumental, and he approached this new challenge with his characteristic curiosity and rigor. Based on his intuition, Galileo believed that the fastest path would be an arc of a circle. This idea was rooted in his deep understanding of motion and geometry. It seemed logical, a smooth, continuous curve that connected the 2 points with minimal deviation. The circular arc appeared to be the most efficient path, minimizing the distance the bead would need to travel. However, Galileo's intuition, though groundbreaking in many ways, led him astray in this instance. The true solution to the problem was more complex and elegant than he had imagined. Unbeknownst to Galileo, the solution to the Brachistochrone problem lay not in a circle, but in a more elegant curve, the cycloid. This curve, which is traced by a point on the rim of a rolling circle, was the key to solving the puzzle. This cycloid curve, with its unique properties, held the key to unlocking a deeper understanding of motion. It paved the way for the development of the principle of least action, a fundamental concept in physics that describes how objects move in the most efficient way possible. The Brachistochrone problem, therefore, was not just a mathematical curiosity, but a stepping stone to greater discoveries in the realm of physics. The Brachistochrone problem, though seemingly simple, remained unsolved for years after Galileo's attempt. Galileo, with his pioneering spirit, had laid the groundwork, but the intricacies of the problem eluded even his brilliant mind. His initial efforts, though insightful, were not enough to crack the code of the fastest descent. It was not until 1696 that Johann Bernoulli, a Swiss mathematician, issued a challenge to the intellectual giants of his time. Bernoulli, known for his audacity and sharp intellect, saw an opportunity to push the boundaries of mathematical thought. He believed that the Brachistochrone problem held the key to unlocking new realms of understanding in physics and mathematics. Bernoulli, confident in the elegance and power of the Brachistochrone problem, sought to ignite a mathematical duel, inviting the likes of Isaac Newton, Gottfried Wilhelm Leibniz, and other leading thinkers to solve it. This challenge was not just a test of skill but a call to arms for the greatest minds of the era to engage in a battle of wits and intellect. The response was electric. The mathematical community was abuzz with excitement and anticipation. Scholars from various corners of Europe, driven by the thrill of competition and the desire to achieve intellectual supremacy, eagerly took up the challenge. Mathematicians across Europe, spurred by the challenge and the allure of outwitting their peers, raced to find the solution. The problem became the focal point of countless discussions, debates, and late-night study sessions. It was a time of fervent intellectual activity, with each scholar hoping to be the first to crack the elusive code. Among them was Isaac Newton, who, though retired from public scientific debate, could not resist the allure of a good puzzle. Newton, with his unparalleled genius and relentless curiosity, saw the Brachistochrone problem as a worthy challenge. Despite his retirement, the problem reignited his passion for discovery and innovation. Legend has it that Newton received Bernoulli's challenge late in the afternoon and, fueled by his legendary focus, solved it before dawn. This tale of Newton's overnight triumph has become a testament to his extraordinary intellect and determination. It is said that he worked tirelessly through the night, driven by an insatiable desire to conquer the problem. Newton, in his characteristically cryptic fashion, submitted his solution anonymously. His decision to remain anonymous added an air of mystery and intrigue to the unfolding drama. The mathematical community was left to wonder about the identity of the brilliant mind behind the solution. However, upon seeing the elegant and concise proof, Bernoulli is said to have exclaimed, "I recognize the lion by his claw." This exclamation was a recognition of Newton's unique style and unparalleled genius. Bernoulli's acknowledgement of Newton's work was a moment of profound respect and admiration. The solution, as we now know, revealed the cycloid as the curve of fastest descent, proving Galileo's intuition wrong, and opening the door to a deeper understanding of the principles governing motion. This discovery was not just a mathematical triumph, but a pivotal moment in the history of science, paving the way for future advancements in physics and engineering. Section 4. Hero's Insight, the Straight Path of Light. The idea that nature seeks efficiency is not new. Long before Galileo, Bernoulli, or Newton, ancient thinkers observed similar patterns in the natural world. One such observation came from Hero of Alexandria, a Greek mathematician and engineer living in the 1st century AD. Hero, known for his inventions and ingenious contraptions, also made significant contributions to the field of optics. Hero observed that light, when reflected off a surface, always takes the shortest path. This observation, now known as Hero's principle, explained why the angle of incidence equals the angle of reflection. It seemed that even light, a seemingly intangible phenomenon, adhered to a principle of efficiency. While Hero's principle applied specifically to reflection, it hinted at a broader principle governing the behavior of light. The shortest path, however, is not always a straight line. This realization would come centuries later with the work of Pierre de Fermat, a French mathematician who would revolutionize our understanding of light and pave the way for the principle of least action. Section 5. Fermat's principle: time, not distance. In the 17th century, Pierre de Fermat, a French mathematician with a keen interest in optics, made a groundbreaking discovery that would forever change our understanding of light. Fermat realized that light, while always taking the path of least time, doesn't always travel in a straight line. This realization came from observing the phenomenon of refraction, the bending of light as it passes from one medium to another, like from air to water. Fermat noticed that light doesn't always take the shortest distance when refracting. Instead, it takes the path that minimizes the time taken to travel between 2 points. This is because the speed of light changes depending on the medium it travels through. This profound insight, known as Fermat's principle of least time, explained why a straw appears bent when partially submerged in water, and laid the foundation for understanding lenses, prisms, and other optical phenomena. It also hinted at a deeper principle governing the behavior of light, a principle that would later be generalized to encompass all of physics. Section 6. The cycloid's triumph, connecting Fermat and the Brachistochrone. The connection between Fermat's principle and the Brachistochrone problem might not be immediately obvious, but it lies at the heart of the principle of least action. Remember, the cycloid, the solution to the Brachistochrone problem, is the curve of fastest descent. But why? The answer lies in Fermat's principle. Imagine the bead sliding down the wire as a beam of light, traveling through a medium where the speed of light changes continuously with height. The cycloid, it turns out, is the path that minimizes the time taken for the light to travel from the starting point to the end point. This realization was a pivotal moment in the development of the principle of least action. It showed that Fermat's principle, initially applied to optics, could also be used to understand the motion of objects under the influence of gravity. This connection suggested a deeper, more universal principle at play governing both light and matter.